Good evening. I'm Samuel Sivi, coordinator of the Young Actuary Initiative, and I am delighted to be with you tonight for our second webinar of the French Young Actuary French chapter. It is our great pleasure tonight to welcome Simona Mailer, winner of the 2024 SCORE Actuarial Prize in Switzerland for a PhD thesis completed at ETH Zurich, Tropical Cyclones, Displacement and Policy, Advancing Climate Risk Assessments. She is now a postdoctoral researcher at Stanford University. And Simona, the floor is yours now.
Thank you for the introduction. I'll pull up my slides. Okay, so yeah, good evening. Welcome also from my side. My name is Simona Mailer. I'm a postdoc at Stanford, and I'm going to talk about tropical cyclones, human displacement, and policy. So this is work that comes out of my PhD, but then also some of the postdoctoral work that I have been doing in the past few months. And I would like to start my short presentation, or not so short presentation, with an image of the destruction that Hurricane Otis brought to Acapulco in Mexico over a year and a half ago. And I think this image is a great illustration for my field of research. As a weather and climate risk modeler, I'm interested in how we can model and understand the interplay of such extreme events with society, but also how extreme events change in the future and what this means for the system exposed to them. So my research, broadly speaking, ranges from these foundational aspects of climate risk modeling to translating my knowledge also to people on the receiving end of climate risk information, also in the context of decision making. So on a daily business, I use climate risk models, and you probably know these are somewhat of a concept of modeling risk or impact as the interplay of hazard, exposure, and vulnerability. And the specific climate risk model I'm using in my work is called Climata. It's an open source, open access, probabilistic climate risk modeling platform that is available through GitHub. And it's also a model that at ETH Zurich, we all co-develop and maintain on this platform. So today I'm showing three to four applications of this climate risk model in my research. I'm going to start with tropical cyclones first, a model in the comparison of different tropical cyclone models. And then I'm switching to uncertainties in tropical cyclone risk modeling, so along the entire risk modeling chain. I'm then showing an application of these climate risk models in the context of human displacement, so no longer quantifying damages in terms of financial losses, but actually quantifying how many people are being displaced as a consequence of extreme weather events. And then finally, I'm showing some work in collaboration with social scientists where I've investigated the relationship between extreme weather events and climate policy support. So starting with the first part on tropical cyclones, going back to the example of Hurricane Otis, what you see here is the historical record of tropical cyclones in the area of Acapulco. And you see that this is very sparse. Since the 1950s, there have only been 8 storms recorded in this area. So I think this really clearly shows a challenge that we often have where the number of observations is far too sparse for reliable risk assessment. And the solution to this data sparsity comes in the form of synthetic modeling, in which larger data sets of tropical cyclone behavior are created, and these can then be used as inputs for climate risk assessment. So very at the beginning of my PhD, I was interested in how do these different tropical cyclone models, and I'm speaking about the ones that are academically available, not necessarily ones that the industry uses, because these are not usually the ones that I get my hands on. But I was interested in using these academically available global tropical cyclone models and test how they perform in this impact and risk assessment. So I brought together these tropical cyclone modelers and performed this modeling and comparison study. And specifically, I used, first of all, the historical record, which is called IB-TRACS, and then a probabilistic set of tropical cyclones, which are derived from the historical record, and then 3 additional synthetic models called STORM, another model from MIT, so Kerry Manuel's model, and then a third model, which is called CHAS from the Columbia University. And I used these together with a parametric wind model to generate hazard sets and use with a spatially explicit representation of asset values for exposure, and regionally calibrated impact functions on the side of vulnerability to calculate direct economic damages coming from these various event sets. So what I'm showing you here is a common tool in risk assessment, which are impact return period curves. And you see here the results for the 5 hazard sets for the North Indian Ocean. This is present day risk. So I used event sets that were generated from the 1980s to like 2020. And for example, if you look at this graph and compare the estimated impact for the 100-year event, you see that there are notable differences between these track sets, where you have the probabilistic IB tracks that yields a number of 40 billion US dollar, and you have Storm that yields an impact of 246 billion US dollar, which is a notable difference. Maybe also going back to the fact that the historical record is too sparse. I think this also comes out nicely out of this graph, that with 39 years of historical observation, you really don't have the data set or the statistical power to derive something like the 100-year event without additional extreme value analysis or something like that. And this was really just a quick glimpse into some of the results that I generated for this model and the comparison on the risk or impact level. I think when I did this, I often was asked the question, so which is the best model? And my usual reply was that this depends on your application. So I think I sensed there was a need in like translating this quantitative type of the analysis with my understanding of some of the model qualities, and also intersect that with possible applications to then guide users in finding the best model for their application. Now kind of like moving from this first assessment of tropical cyclone like uncertainties in the hazard set choice and direct economic damages in the present, I was interested in thinking about how tropical cyclone risks change in the future with climate change and with socioeconomic development. And I was also interested in understanding how all these like different layers that come together if you model future climate change and future socioeconomic development, how this unfolds on the risk level. So I started a project on uncertainties and sensitivities in future tropical cyclone risk assessment. And to do that, I used global sensitivity and uncertainty analysis. And kind of like a key step for this work is defining the input factors, so the input parameter space that I would vary and then translate or propagate through the risk modeling chain. And what I did in the first step was using one of the synthetic tropical cyclone models. In that case, I used Carey Emanuel's MIT model, and that just took all possible combinations of event sets downscaled from different climate models for different emission pathways. I used 2 different wind models, and then used a subsampling routine to kind of like test uncertainties on the hazard level. I repeated a similar approach on the exposure, where I used different GDP scaling factors for my spatially explicit map of asset values according to the 5 differentiated socioeconomic pathways. And I also used a different weighting of urban and rural kind of like factors to test a bit the sensitivity of how do impacts change with these differences. And then for vulnerability, I think that was the trickiest part, because we don't really have the means to model future vulnerabilities, and we don't really have a set for future vulnerability functions. So instead of trying to imagine what happens in the future and possibly how these vulnerabilities changed, I simply used a wide range of a calibration kind of like range to inform uncertainty in the impact function itself. And then with all these ingredients, I repeated the risk kind of like calculation thousands of times, so more than 20,000 of times. And what you get out of that is then not a single number, obviously, but a full distribution of possible outputs. And because I also separated kind of like the risk drivers in the sense of which part of the future risk can be attributed to climate change, which part can be attributed to socioeconomic development, and then how do these 2 components translated into a total risk change. That's kind of like the first part of the analysis. I then looked at this total risk change and evaluated the full range of the uncertainty distribution. which is the uncertainty analysis. And then finally, I asked the question, which of all these possible input factors that I listed on the left of this slide explain how much of the resulting uncertainty, and that is the sensitivity analysis. So I'll walk you through a couple of these results. And what I'd like to show first is simply this uncertainty output. So what you see on this graph is the expected annual damage change by 2050 in the Western Pacific. And again, it's not a single number that I would say your risk changes by 10 or 20%, but it's now a distribution of your risk changes somewhere between not at all to up to 50%. And I think that the first kind of like thing I would like you to draw your attention to is the location of the peak, which is where the model output lands most frequently. And that is actually a value that is pretty moderate, where we model something like a 2.5% change in risk by 2050. But I think the more interesting part is that, yes, some of these model values go up to much higher values. And the question then is why? Why is that? Why do we have such an uncertainty that kind of like extends up to some very high values for some of the model input combinations? And kind of like the answer to this question comes in the form of the sensitivity analysis. And what you see here are the sensitivity indices. So this is a value that just kind of like explains the width of each of these bar plots, basically explains how important the respective input factor is for explaining the output uncertainty. And I think the picture here is pretty clear that you see all orange on this slide, which means that the GCM, so the global climate model that I chose for the downscaling of the TC event sets, was the most dominant factor in contributing to that uncertainty. So I was like, okay, this is an interesting finding. I now understand that this entire uncertainty that I show here, or almost the entire uncertainty that I show here, can actually be attributed to the global climate model choice. So what I did was kind of like converting this same graph. So it's still expected annual damage changes. Now I flip them to the y-axis, and I separate the full uncertainty space into contributions from the single global climate model outputs. And I list these global climate model outputs by climate sensitivity. And I think that was an interesting finding for me, to find that there is a positive relationship between the climate sensitivity of the GCMs that I choose and the modeled risk increase. So global climate models with a low climate sensitivity yield a low risk change. And in contrast, global climate models with a high climate sensitivity yield a much higher potential risk change. You also see in the far left there is an outlier, as so often one of the models did not behave as expected. But at this point, I was like, okay, this is interesting, and I wonder if this is something that is generalizable beyond the MIT model or not. And luckily, I'm in a position to answer this question because I had access to not only the MIT model, but all the other models that I compared for the modeling the comparison as well. So I repeated that whole analysis of uncertainties and sensitivities for 3 additional models as well. So I also included the chess model storm and the probabilistic IB tracks in this modeling setup. And because they all vary slightly in their formulation, in their setup, I could not define the exact same definition of input factors. But for each of these models, I would just kind of like vary them across a similar range of input factors and then repeat the uncertainty quantification for each of the 4 models. And now what you see is the same graph. It's the change in expected annual damage in the Western Pacific. What you see in blue is the results of the MIT model that I showed before. And the 3 additional kernel density distributions are now shown in orange, green, and purple. And again, looking at the locations of the peaks in this distribution, you actually see that all 4 models aligned pretty well in their estimated kind of like where the model output lands most frequently. So all the models predicted a risk change of 1 to 2.5%. But I think the more interesting piece is that these full distributions of the models are actually quite different, especially the MIT model behaves somewhat differently than the other 3 models. And this is an insight that I would not have gained without this uncertainty quantification. So, and maybe also in contrast a bit, what I showed you before was like the MIT distribution only. And if I wanted to plot the full distribution of the MIT model together with the other models, I would need to extend the x-axis to much higher values. So you really see that this relationship in this visual quite notably. So going back to the sensitivity indices, this is the result that you saw before, where for the MIT model, the climate model choice is the dominant source of uncertainty. Now, including Chasterm and the probabilistic Ivy tracks in this graph, the picture looks quite different. And it's not so clear that we can say there is a single input factor that explains most of the output uncertainty. I think for the most cases, it's this input factor that I call SSP exposure, which is basically the GDP scaling factor that I apply to each of my exposure points to simulate socioeconomic change. And this socioeconomic change, according to the 5 different shared socioeconomic pathways, in the case of these 3 models, explains a lot of the resulting output uncertainty, but there are other factors that contribute to it as well. And maybe just I understand that this is a very information dense plot. So the single bars or like the plot is organized by you have the different models in the columns. You have 2 rows for the 2 future time periods where you have 2050 on top, the end of the century at the lower row. And then the single bars show 4 global regions. So I have North Atlantic, Eastern Pacific, North Indian Ocean, Southern Hemisphere, and Western Pacific. And I have 2 bars for the change in expected annual damage and the 100-year event. But basically, yeah, the message that I would like you to take home from this is that for the MIT model, we have a clear dominating source of uncertainty. For the other 3 model, not so much. Yeah, and then going back to this question of whether this relationship between the climate sensitivity in the GCMs and the resulting risk increase can be extended beyond the MIT model or not, I could answer by repeating the same analysis with the CHAS model, which is also a statistical dynamical model as the MIT model. So a very similar model setup. And the simple question to that is no. If you use CHAS, then there is not such a clear relationship between the climate sensitivity and the resulting risk increase. And I think the main reason why not is that CHAS uses inputs for their intensity modeling that are beforehand to some degree bias corrected, whereas the MIT model, or like GCM bias corrected, and the MIT model does not do that. So I think it is always important to understand which of the modeling findings hold for statements that are true for beyond the model boundaries and which are really just a finding that are like valid for within the model boundaries. And with that, I think I already hinted at this aspect of translation that I always try to do in my work, where I was actually thinking about, so I have a wide range of uncertainties and what do I do with this information? I now understand where this uncertainty comes from to some degree, but it's a bit of a so what, how can we make use of this type of analysis? So what I did in an initial step to kind of like start structuring the uncertainty was introducing classes of uncertainty. So I would use the understanding of whether the uncertainty comes from an aleatory source, so the pure randomness in a system, whether it comes from epistemic sources, which is basically the knowledge gap, or whether it comes from normative choices, which is kind of like the value-based decisions that we introduce when we do anything. And then I kind of like having these classes and knowing which of these sources can be reducible or not is then kind of like a first guidance to, okay, maybe you should invest more research in better understanding some of the knowledge gaps between the tropical cyclone models, because this actually means we can reduce the uncertainty. If you speak about, I don't know, a source of aleatory uncertainty, this is something you cannot reduce by definition. So it's basically not something you can address with more research. So having these angles and this structure of different classes of uncertainty then helps derive implications for model improvement or decision making. And yeah, kind of like wrapping up, I think a core finding is that we have variable uncertainty sources depending on your risk model setup and hazard model choice. Also, I think this application of uncertainty and sensitivity quantification is a really transparent way of disentangling all the possible sources of uncertainty and also showing wide ranges of possible futures. I think we usually kind of like default to averaging things out and providing best guesses. But if you think about risk and really want to understand what might happen in the future, I think this is a very potent way to show a wide range of possible futures. And then thinking about this range of uncertainties, maybe towards decision making, you could start using levels of cautiousness and risk aversion to then think about how do you collapse or not this uncertainty space in the context of decision making. And finally, having these three classes of uncertainty helps kind of like structure that output space in a more meaningful way. So now moving from a lot of tropical cyclones and uncertainties and impacts in financial terms to using the same approach of natural hazard risk modeling, but this time applied to the challenge of human displacement. And I think this is work I did together with a couple of collaborators, most notably the Internal Displacement Monitoring Center in Geneva and the United Nations University in Bonn. And the Internal Displacement Monitoring Center in Geneva is the instance who collects reports for internal displacement. And basically, displacement is defined as the involuntary character of a movement within national borders. So this kind of like captures all the people who are forced out of their homes after extreme weather events. So this is what you see on that picture in the blue bars called disasters. But then basically the IDMC also collects data on conflict and violence related displacement. So in my work, I did not look at the conflict and violence related part, but we used these climate risk models to assess disaster related human displacements. Going back to kind of like the risk model setup, what now changes to my tropical cyclone work is that I work with 4 different hazards. I have a slightly different exposure where I have kind of like different structural building types and then a country's population apportioned to these different structural building types. And because I have different structural building types, I also have vulnerability functions for all these different building types. And then how we approximate the human displacement is that we calculate a level of structural building damage, which is between 0 and 100%. And then we set a threshold and assume that people are leaving their homes upon like a certain threshold of building damage. In a bit more detail, we look at tropical cyclones, coastal floods, river floods, and droughts at a global scale. As I said, the exposure model I use is called Billing Exposure Model. It comes from the United Nations Environment Program, and they kind of like it's a big data set. It has a lot of information in terms of it has population data, it has these different structural building types. It also has information on different sectors and basic services. And we just use the first two to then generate this geospatial exposure layer that we would work with. And on the side of vulnerability functions, because we have so many different structural building types, we also need the equivalent number of different vulnerability functions. And this is really just an illustration that for tropical cyclones, for example, we always have this like sigmoid shaped impact function at the base, but then depending on what structural building type you talk about, the exact parameterization of the impact function shifts slightly. So now showing you a couple of results again from this piece of work. What you see here is a global map of annual average displacement from the 4 hazards combined at the admin 1 level. So I think a nice piece of our work was that we calculated results at the administrative level. So you really have a level of granularity that also comes out where you see regions in the world that are at high risk for human displacement and other regions which are at lower risk for human displacement. And I think kind of like starting with this global map of all the hazards combined, I now work through a few of the SAP analysis that you can conduct with our risk modeling setup. So first, what I show here is again the annual average displacement now split up by the 4 hazards that we have. And actually I'm showing national level numbers. But basically what you see is that depending on your hazard, you have, first of all, different numbers of expected annual damage, annual average displacement. But also the hazards are different. So tropical cyclones only show up in the tropics and subtropics. Coastal floods are obviously limited to the coast. And then I think river flood and drought are somewhat more uniformly distributed, so they affect wider parts of the world. And I think with that understanding, it's nice to know which areas of the world are most at risk from tropical cyclones compared to flood or drought. And I think these maps are a good starting point to have the conversation. Then obviously the question is always, how do these risks change in a changing climate? So what you see here is the annual average displacement changes by the end of the century. And you see that depending on your emission scenario, whether you use an optimistic or the numbers in brackets show a pessimistic scenarios, you actually see a pretty different risk increase. You also see that tropical cyclone risks and coastal floods uniformly increase. So there is no risk decrease in the future for these hazards, whereas for river floods and droughts, you have some parts of the world that actually see a risk decrease, for example, from droughts, and other parts of the world see a risk or a displacement risk increase from droughts. And going from this like global picture type of analysis to more regional level, we can again go back. Maybe to one example, what you see here is, I just picked Afghanistan. What you see here is displacement risk from river floods. You see that the present day displacement risk in Afghanistan is 48,000 people being displaced. You also see that in the future, under an optimistic and a pessimistic scenario, most areas in Afghanistan see a risk decrease. So that's actually good news. We find regions in the world that have a lower risk for displacement in the future just because the hazard changes. I think, of course, there's a twist to this story because I wouldn't be showing this otherwise. With our model, you can also look at, for example, drought risk in the same reason. And I think this is telling because on the one hand, you have a risk decrease from the river flood. If you look at drought, it's already close to double the river flood risk in the area today. And then in the future, this risk changes quite drastically. So we expect a lot of people being forced out of their homes for reasons of drought in the future. And I think this is really just one example where having this global like skill of having different hazards, having the future climate simulations, but then also the ability to zoom into more regional aspects can just add a nice tool and database for some of the questions that you might consider also at a more regional level. And then in this final piece, I would like to talk about one of the model limitations. And because maybe from the first part of my talk, you sense that I like uncertainties or I'm interested in what these mean in the modeling world, I'm going to show you a sensitivity analysis here again for two of the hazards. On the top row, you have the tropical cyclones. On the bottom row, you have coastal flood. And you have the result for the present day in Vietnam. And what we know is that our approximation of modeling human displacement simply as people being forced out of their homes upon a certain building damage threshold is extremely simplified. And we also know that setting this threshold is crucial, and picking a threshold is not easy. So we built on existing literature and normally chose this 55% damage threshold, which you see in the middle column, because this is what has been done in previous work, but we also felt that we at least want to test what would happen if we lower this threshold and assume that people are leaving their homes already upon a 30% structural damage threshold, or what happens if they could stay in their homes up to a 70% structural damage. And basically the numbers differ quite widely, and especially they differ notably for tropical cyclones, which yields a factor of difference between the lowest structural building damage and the highest of close to 300. For coastal floods, it's also notable, but not as extreme. And I think the reason is because we have these like sigmoid-shaped impact functions, and if you vary this threshold just a bit, you actually have a huge response in the resulting impact that you exactly see with these maps. And I think this really hints at possible future research for future improvements that we could invest in better understanding modeling of human displacement. So wrapping up this part, I think what I showed you is this like forward-looking risk-informed approach to displacement, and this is in a wide way like complementary to all the reporting and data collection that the IDMC does. So it really just offers an additional lens to the problem of human displacement. And we did this using a modular fashion, open source and transparent modeling, so that we can constantly improve on these pieces. And you've probably guessed that there is a lot of room for improvement. So the key challenges that we faced when setting this modeling chain up was this, as I said, this threshold is somewhat arbitrary and has a huge influence. We also approximate, at least for tropical cyclones and coastal floods, displacement as a direct consequence of the loss of home. You can also argue that there are more indirect effects like losses of livelihoods or losses of access to basic services that also influence whether people flee their place or stay put. And there is also some people who would have the need to leave, don't have the ability to leave. So there are a lot of underlying socio-demographic factors that shape the actual displacement on the ground, but that we cannot currently model to the degree that we wish. Also, I think a big challenge is model evaluation. We only have a very short observational record from the IDMC database, and there is a lot of like issues with data cleaning and reporting biases and so on. So there's not even a good database to better calibrate these models. And also in terms of data quality, some of the underlying exposure maps that we use sometimes have a bit of outdated exposure numbers, just because population growth in some parts of the world is so dynamic and high that if you have an exposure layer of 5 to 10 years old, that is widely outdated. So I think we could do better on that end as well. And I think this, already links to future research agenda, where including some of these like aspects of underlying social, political, demographic, economic factors would certainly improve our understanding of displacement. Also including additional hazards is always a topic. And then some people, especially from the United Nations side, were interested in quantifying the losses or kind of like the costs associated with displacement, because this then feeds into some of these international negotiations around loss and damage, for example. Okay. I'll move to the third part of this talk, which is more kind of like the policy related piece where, this is about the relationship between extreme weather events and support for climate policies. And this is a collaboration that kind of like started with a social scientist. So my colleague, Victoria Colonia, does a lot of behavioral studies, and she collects a lot of like global survey data, in this case, from over 68 countries, and she got responses from close to 72,000 people distributed over these 68 countries. And she asked questions related to climate policy support, to trust in science, to just a wide array of somewhat climate related or behavioral related questions. And at some point she came up to me and was like asking whether I think that we could collaborate, because she was looking into how people think they're affected by extreme weather events, and whether they think that this is related to climate change, and then how this translates to their, like how these beliefs translate into political and like voting behavior. And she was wondering if their beliefs are somewhat grounded in the exposure. So if people who believe they're affected by climate change are also the same people who see a lot of extreme events in their daily lives. So this is how we came to collaborate, because the exposure to extreme weather events is something that I can do and I can model. So we did this study, which is basically we have a hypothesis of, we think people who attribute extreme weather events to climate change, and this is the social sciences part, and then people who live in countries with higher exposure to extreme weather events show stronger climate policy support. And what I'll do for the next couple of slides is show a series of questions that help us test this hypothesis and show then also the results that we found from it. So starting with this first question of what is the level of public support for 5 different climate policies across these 68 countries. And this is a question that Victoria could answer with the data from her survey, where she asked people to rank kind of like if they're in favor of certain climate policies or not, from very much to not at all. And she gave them 5 different climate policies. Basically, what you see from these bars is that most people in general support climate policies. You also see that carbon taxes, so the top row with the least purple are the least favorite form of climate policy, where the lowest climate policy is protecting forests and land areas. That is the most popular. So it's kind of like an obvious thing. People don't really like taxes, but they're always in favor of protecting forests. But basically what happens if you condense these 5 climate policies into one index and then map this on across these 68 countries, you see that, well, first of all, good news is the vast majority of the survey respondents support climate policies in all of the countries. You see that the highest support, which is the color more towards the darker purple tones, comes from Asian countries and African countries. You see average climate policy support across, for example, Australia or the UK, and below average climate policy support in some of the European countries, like Finland, Norway, and some of the northern countries. That linked to this is the question, to what degree do people attribute extreme weather events to climate change? And then also, is this subjective attribution related to climate policy support? So for the first part, to what degree do people link extreme weather events to climate change? And I think this is kind of like the results that you see here, again shown on the global map. And you see there is no green colors, so there is always a positive subjective attribution, and all of the countries or people in these countries actually link extreme weather events to climate change. You see that this subjective attribution is highest in some South American countries, especially Brazil, Colombia, and Bolivia, and lowest again in the Northern European countries and some Asian countries. And then the second piece to the question of, does this subjective attribution predict climate policy support? The simple answer here is yes. You see that all of the 7 different extreme weather event types score much above the 0 line. You also see that there is some slight variation across the different hazards. For example, you see that there's a slightly lower score for wildfires, a slightly higher score for heat waves. But basically, subjective attribution is a good predictor for climate policy support. Then is kind of like the part that is more home to my natural science component, where we're asking the question, does exposure to extreme weather events on the population relate to climate policy support? And for this piece, I generated a metric out of 20 years of extreme event data for 7 different extreme event types. And I basically calculated the average annual proportion of a country's total population exposed to each hazard. And this is a relative metric. I think the good thing about this relative metric is that I can then compare the different hazards with each other. There are obviously flaws in choosing such a metric, but basically we calculated this relative metric for the entire countries. And as you can imagine, if you look at the US, for example, you expect a lot of wildfires in the West and a lot of maybe tropical cyclones in the East. So what happens is that the US scores high for both hazards, even though some people in the East might not see wildfires, and on the opposite, some people in the West might not see a tropical cyclone. But that being said, we use this relative measure of exposed population to extreme weather events to then also ask the question, does the exposure relate to climate or predict climate policy support? And the simple answer here is no, not really. All of the results are kind of like centered around this zero line. And I think what this tells you is that the mere exposure to these extreme events does not predict climate policy. There are a couple of like little details where, for example, there is a negative relationship between the exposed population to heavy precipitation and policy support. And this is kind of like the light blue dots that you see in the middle. Our hypothesis is that this is often because heavy precipitation events are in the media not directly linked to climate change. So people don't make the connection from a lot of rain to climate change. I think people much rather make a connection from high temperatures to climate change. And another finding that we see here is the dot on the far right, which is wildfires, where there is this positive relationship. And the hypothesis there is that wildfires cause a lot of visible damage. So people are more likely to actually attribute that to climate change. But these are all hypotheses and obviously need more research to be confirmed or not. But then the last part is, so what we looked at so far is just the exposure and the relationship to climate policy support. So there is an additional layer where the question or the hypothesis is that the relationship between exposed population and climate policy support is stronger for individuals with higher subjective attribution. And I think this is an interesting interaction term with also mixed results where this hypothesis is wrong for drought, floods, and wildfires. And we were also, again, thinking about why is this not true? One hypothesis or possible explanation is that these are all extreme weather events that have a management component where you could irrigate kind of like your agricultural fields in response to drought. There is flood protection mechanisms, and you can fight wildfires. So there is a human component to these extreme weather events that maybe inhibit this kind of like the stronger effect of the subjective attribution in predicting climate policy support. In contrast, for heat waves, heavy precipitation, and storms, there we see a positive relationship, and we hypothesize that these are hazards that have no kind of like human control to them. Once they're here, you cannot really stop them. You can go inside and use AC to protect from heat waves, but there's not really anything that turns the temperature down in the event of a heat wave. The same for storms. Once a storm approaches, you can go protect yourself, but you cannot kind of like stop the storm. So this is kind of like what we might think is a cause for the different relationships. So finally, to go back to the initial hypothesis that we expect stronger climate policy support from people who attribute extreme events to climate change, this part of the hypothesis we could confirm with our results. So yes, this is true. The second piece, we expected stronger climate policy support from people who lived in countries with higher exposure is actually false as such. And I think this is an important piece, especially for me as a natural scientist who works with extreme weather events all the time. I think for me, it's kind of like a logical thing that people who see more of these extreme weather events should also be more in favor of climate policies. I think what really matters is what in the end people believe. So if people believe they're affected by climate change, they're more likely to support climate policies. If they don't believe they're affected by climate change, then they're not really receptive to any climate policies. And I think this is actually an instance where we have some leverage in increasing climate policy support by better communicating the links of these extreme weather events to climate policies, to climate change. And then finally, kind of like in terms of outlook for this piece of work, we included extreme weather events over a period of 20 years, just because we also needed a robust enough sample to test this. But we know that there is something called recency bias, where people are more likely to remember events in the recent past than in the far past. So we're looking into a temporal proximity of single extreme events in their influence of climate policies. And then also the same holds for extreme event severity, where maybe some regions see kind of like small, moderate events pretty frequently, but they're just too small to really leave an imprint in people's maybe climate policy support. Whereas if you have a really big, strong event, then this may influence your climate policy support more strongly. So these are two examples of future research that we plan to work on. Yeah, and I think this brings me to the end of my presentation, where I gave you a rough outline of my research, which goes from tropical cyclone related questions, especially around uncertainties in modeling of future risks, to this whole topic of human displacement as a consequence of natural hazards, and then finally this link to using some of the climate risk information in the context for policies. And yeah, I thank you very much for your attention. I'll stop sharing my slides, and then I think I'll go look at the chat for questions. Yeah, I think you're invited to ask questions if you have right now in the chat. I see no questions, so either everything was so confusing that you have no questions, or it was all crystal clear. Okay, I see one question. So one question is a possible correlation between climate risk models and GDP models taken into account in the study of change in risks? That's a good question. And I actually did take this into account and also not. So the results that I showed you today was I would vary the change in the climate risk models and the GDP models independently from each other, and then just look at a full spread of resulting outputs that you could possibly have. But what I also did for my own understanding is, for example, only using the spread of I would say like emission scenarios for the climate model. So whether you're on an emission scenario on a path, I don't know, like RCP 8.5 or 4.5, and then using that in combination with the respective shared socioeconomic pathway, which would be SSP2 or SSP5, and then how this maybe limits the range of the possible outputs or not. And I think because my question was trying to understand what leads to a wide range, or what leads to the uncertainties, I in the end decided to look at a full range of possible futures, also because it's not so clear that this relationship is always a given. So it's not so clear that the SSPs, which is in that case the GDP models, are directly linked to the resulting emission pathways or vice versa. So I looked at this relationship, but in the end decided to rather explore a wide range instead of focusing on single scenarios. And then there's another question which is related to whether I have modeled any secondary perils in my impact studies. So for example, storm surge or precipitation for tropical cyclones. And this is also a very good question. And this is something that I started doing at some point during my PhD, because I was interested in this question also of how does the entire risk kind of like change if you include these water-related hazards. So I did preliminary studies for some single regions, and I have to say, I think you probably know that as soon as you include the water-related hazards, you have to deal with hydrodynamical modeling, and then things get very computationally demanding and expensive. So in the end, I'm not explicitly including them at the moment. I, in a way, implicitly include them by using impact functions that were calibrated to total damages. So using wind as a proxy, at least for storm surge, seems somewhat reasonable. But I'm also aware that especially with precipitation, we probably see kind of like future shifts where wind is no longer a good proxy for the entire damage. And this is certainly something that I think we should look into more in the future as well.
Okay, so thank you very much, Simona, for this presentation. That was enlightening. And the video, if you want to have some more reference, the video will be online in a few days on ActuView and on our YouTube channel. And the presentation will also be available on the Institut des Actuaires website. And we'll see you in a few days for the presentation, for another presentation from the winner for the prize in Sweden. So thank you very much. Thank you, everyone. And thank you, Simona. Bye.
Bye.
Bye.